Well, you might have seen the video of the water tank that just took off and landed in a different location to where it started. It's a pretty dramatic event, and yet it's surprising how little it takes to achieve this. In order to get an idea about what sort of pressures are required to lift a tank like that, you could just ballpark estimate how much force is required by equating the upwards force given by the pressure times the area of the roof of the tank with the weight. So you equate the weight, which is the mass times the gravitational constant, you equate that to PA, which is the pressure times the area. In fact, I've been involved in a case like this before where the tank took off and pulled out its concrete foundation ring, sheared off all these bolts, steel bolts. The tank itself maybe weighed 350,000 kilograms and the concrete ring about another 150,000. So the total was about 500,000 kilograms. And the force was just that times 9.81 meters a second. So that's the force required to balance the weight of the tank and the concrete ring. So the area of the roof of the tank is just pi r squared. And the diameter is 35 meters, so the radius is about 17 and a half. So you equate P, which you're trying to calculate, times pi times 17 and a half meters squared for this 35 meter diameter tank, equal to 500,000 kilograms times 9.81 meters a second. And the required pressure would then be, of course, 500,000 times 9.81 divided by the area, which is pi times 17 and a half squared. That gives you 5,000 pascals, 0.05 bar. When I first did this calculation many years ago for this tank, I couldn't believe how low this pressure was. 5,000 pascals is really quite low. And so I did it 2 or 3 times. Of course, I got the same result, but that's how little it takes to lift up a massive tank and its foundation of this size. Of course, you cannot get to a situation like this before you shear off the bottom of the tank, because as long as the tank is fully sealed, the overpressure just tends to expand the walls of the tank. The floor has to drop out before it takes off. And the bottom of this particular tank was a 1 centimeter thick, 10 mil thick steel plate that was sheared off in this manner from the side walls of the tank. Very much like, you know, these old can openers. You see these vintage can openers that open these cans. You see the top of the can, how it's sheared off. Very similar to that. But why does this happen? I mean, the pressures cannot possibly be that high. Well, there's a stress concentration on the floor if the roof doesn't frange. So if you don't have a frangible roof, if you don't design a frangible roof, or if you, in this case, it was designed as a frangible roof but not implemented appropriately, the floor will shear off. How does this happen at a pressure lower than the rating pressure of the structure? A building or a tank designed to withstand an internal explosion producing an overpressure of, say, 0.3 bar, fails at 0.1 bar. There's a lot more to this, and that's what we'll be discussing in part 2 of explosions in tanks and chambers. Anybody can press a button and produce results. What you need is the experience and tools to make sense and draw the right conclusions from these results.